Welcome to this next TVB video showcase. This time we'll continue with our previous one where we've simulated a virtual epileptic patient. Here we will follow this article called Individual Brain Structure and Modeling Predict Seizure Propagation, where the authors not only simulated one epileptic patient but 15. So first of all, they had to collect empirical data. Here they show this in figure 1. So they used diffusion-weighted imaging to calculate the structural connectome of each patient, which can be seen here in panel C. In panel B, we have the cortical parcellation, and those red lines, those red stripes, indicate the location of the SEEG electrodes, which would record electrical activity at those positions. And this empirical data can be seen up here in panel A, where they show that for one patient they were able to record symptomatic seizures. Like in this case, there's the seizure-like activity all over the cortex, and also asymptomatic seizures where this hyperactivity is only constrained to some regions. Down here in figure 2, they show their brain network model and simulated seizure activity. On the left, on panel A, we see this brain network model, and the color indicates epileptogenicity. And here, this is different from the subject before. So before we had the subject was focused on the temporal cortex, and now the epileptogenic zone is more concentrated in the occipital lobe. On the right side, we see the simulated time series, and what they are showing is that with one simulation, so without changing any parameters, this model was able to create symptomatic seizures and asymptomatic seizures. On the next slide, we can see the spatial distribution of epileptogenicity for 3 sample subjects. And as you can see, for each subject, they are showing this brain network model, but with different regions which are making up the epileptogenic zone. So now we've already seen this in our first virtual epileptic patient, and now we will switch to the TVB interface. And here I've prepared a simulation already, but this one is different compared to the previous one, because now we are having the epileptogenic zone and the propagation zone more in the prefrontal cortex compared to the other simulation where it was the temporal cortex. So as the simulation is progressing, we can see reoccurring seizures in the prefrontal cortex, pole in this case. Now at the end of this simulation, we will see again a seizure initiated in the prefrontal cortex pole, but this time it won't be asymptomatic or just constrained to one area. No, it will spread through the whole right hemisphere, as you can see. So this simulation should give you an idea of how we can recreate the results the authors showed in their article. Okay, so now it's time to think about how we can treat our virtual epileptic patient. In the real world, when a patient has a drug-resistant epilepsy, one option is the surgical resection of the identified epileptogenic and propagation zone areas. In our simulation, we could do similar. So we have a look at the connectivity of our patient, and we remember that seizures were initialized in the prefrontal cortex on the right hemisphere. So we can show all the edges again. And we have to change the quadrant number 4 for the right hemisphere. And now we want to test 2 different scenarios. So one scenario would be cutting out just the pole, and the other scenario cutting out the pole and the orbital and ventrolateral prefrontal cortex. So these are the edges we want to cut out. And scenario one will be we're cutting out these edges of only one region, and then scenario, we would save this connectivity now, and then we cut out this second one as well, like this, and then save up here again, and then we would use this connectivity to run the same simulation as before, so same local parameters but a different connectivity. I ran the simulation already, and now we will have a look how simulations results have changed. So in this case we are now looking at scenario 2, where we cut out 3 regions. So as the rest of the system stabilizes, we can see there's ongoing activity in those 3 regions with higher epileptogenicity parameter. But because we've cut all edges, this higher activity will never spread through the hemisphere. So we can now switch to the other scenario. In the other case, we did cut only one region, the prefrontal cortex pole, and the other 2 regions with higher epileptogenicity, so the ventrolateral and the orbital part, were still connected to the rest of the network. And we now see if this smaller intervention or smaller resection is still sufficient to prevent the epilepsy from spreading. So what we see now is higher activity in the prefrontal cortex pole, but not in the other 2 regions. So it's not propagating because here we cut all the edges of this region. So we will see hyperactivity in the other 2 regions as well, but we won't see any more symptomatic seizures or complex seizures, which spread through the whole right hemisphere. So this was an example of how to test different scenarios or different possible options for surgical intervention. And we will now switch back to the article, and the authors of the article followed the regions, the 15 subjects after surgical intervention, and then they looked at the outcome. So they also compared the clinical prediction of propagation zones and epileptogenic zones versus the prediction of our brain model. And here in this figure 7, panel A, you can see in red the clinical prediction, and green is the overlay from the model. And as you can see, there are some similarities but also some differences. And on the right side in panel B, they compared post-surgery outcome with the Engel score versus the number of unexplored regions in the propagation zone. So the Engel score is a score for seizure freeness after surgery, and score of number of 3 says that there are still occurring seizures, and a score of 1 is the best score with seizure freeness. And as you can see, the more the 2 predictions differ from each other, so the more the brain model predicts other propagation zones than the clinical expertise, the worse the outcome. So this should give a hint of how such a brain network model can aid to make clinical predictions for epileptic surgery. So thank you for watching, and see you in the next video.